Started. So let's remember last time where we stopped. We stopped where I introduced this mysterious function, area stress function, which if you know that function, which doesn't have much of a physical meaning, if you have this kind of a function and the stresses have the relationships that you see on the board with this function, so basically they are second derivative of this function, they automatically satisfy equilibrium equations. So you don't even have to check. And then what we had to check was whether the compatibility equation is satisfied. So if you take these stresses and put it in Beltrami-Mitchell equation, then we basically arrived at this equation where you have fourth derivatives of this area stress function, as you can see here. And on the other side, that V was what? Do you remember that function V? What was that actually? Potential of?
Potential energy?
Body forces.
Potential, force potential, exactly, for external body forces. So if there is no body force, if there is no external body force, then right-hand side becomes 0, right? And then we saw that if that's the case, if right-hand side is equal to 0, the Laplacian squared of area stress function should be equal to 0. So that equation is called the biharmonic equation. And because of the formulation you see for plane stress and plane stress, plane strain and plane stress, if you don't have any, if V is 0, if you don't have any body force, would the formulation for plane strain be different from plane stress? No, because both of them, the right-hand side will be 0. So the equation is the same no matter if you have a plane stress or plane strain formulation. So what we want to do today is to talk about solutions and solve a few examples to see how this is actually being used or have been used for solutions. And remember that everything that I did was in Cartesian coordinate system. So first we look at Cartesian coordinate system, and afterwards we go back and look at the polar coordinate system. I haven't forgotten about polar coordinate system. It's actually quite important in some practical sense. So what I want to do today is to look at some specific solutions for plane strain, or plane stress, solutions for rectangular domains. Why rectangular domains? Because it turns out that the Cartesian formulation is most appropriate if we actually consider problems in rectangular domains. So we are considering Cartesian coordinates. Okay. And since we want to solve these problems in the class, and you saw that everything becomes very, very quickly complicated, we limit ourselves to the situation when we don't have any body forces. So we really deal with biharmonic equation. So let's write down this assumption. So we assume that body forces either don't exist or they are negligible. So it's useful to, with that assumption, to write down the relationship between stresses and the area stress function quickly. So everything becomes very simple. Sigma xx, we are plane stress or plane strain, so everything is two-dimensional. Sigma yy is similar, the derivative is with respect to x. And then we have sigma xy, which is negative, and the derivative with respect to x and y. Any mistakes? No. Just started. The biharmonic equation. So the governing, so basically the only equation we have to deal with governing the problem then becomes the biharmonic equation, which is I just showed you. Try to see if you remember what this differential operator is actually. How do you expand it? Try to write it from memory. And I write it without talking, and then you can check. So in Cartesian coordinate systems, x and y. Right? So we consider two types of solutions in this class. There are many types, and one type is power series or polynomials. And the other is using the method of separation of variables. So what we first consider is the first one, which is using power series. Maybe I give them one or two. So the first approach is basically making an assumption for area stress function in terms of a polynomial. And I write this this way. So it can be a function of x and y. So if it's a polynomial, it has a coefficient, and then you can have x and y. And this m and n could be any number from 0. They're integers, of course, and it can start from 0. And the domain that we consider is rectangular. And in terms of the solution strategy, last time I talked to you about solution strategies. Does anyone remember those strategies? I told you about 3 solution strategies. Direct method, which was just integrate, And I told you even a simple problem becomes complicated quite fast, so I didn't show you an example. An inverse method and a semi-inverse, where it can be a little bit of this or that. We actually follow an inverse solution strategy. So now you can guess that my next question is if you remember what this was. We did a very small and short example because of course I knew that we have to deal with it. It's a strange solution strategy. In which sense? What did we do? Yes, Gerald.
We started with the solution and worked backwards to find a problem that the solution is.
Exactly. So we start with a solution and we try to find a problem that it fits. So last time I gave you the stress field. So we started from the stress field. When you use area stress function, you start with the area stress function. So then you derive the stresses and then you look at the problem. You try to find the problem that fits it. Now let's do one example which is simple, but let's do it very systematically to understand how it actually works. Last time I just showed you something. I went very quickly so that you can kind of get this concept. But today we actually want to really solve the problem using this method. Now the question is again, where these functions come from. These have been developed through many years, so it takes a lot of experience to understand what solution is good for what problem. So if it is not very intuitive to you right now, don't worry about it. Don't feel depressed. Don't go drinking over the weekend. Everything is okay. It's normal. Okay, so let's look at the first example together. So expect that you need to do some things in the class with me so you don't fall asleep, or I know that it's late in the evening, you all are busy with a lot of things. So now we start with this example. So let area stress function be a function of this form. Why do I write the coefficient like this? It has the same form from that general polynomial equation. There is no x in it, so that's why there is 0 to y squared, and a 0 to is a constant. And I hope that it was clear that in the original formulation that I showed you before, those a's were coefficients that were constant. Now, how strange it is. The question that actually you have to ask yourself in inverse strategy is, what is the problem you can solve with this area stress function? So I write it down. What is the problem that can be solved by this? Okay. So to answer this question, we have to take a few steps. In general, step number 1 is what? Is to check that this is actually indeed a solution to biharmonic equation, right? So the first question you have to ask yourself is, right? Otherwise, this is just a phi. It's not the area stress function. Is it or not? It is. Can someone who hasn't talked in the class so far say why, just without doing any calculation? In English? Like no mathematics. Just conceptual. I mean, there is some things about mathematics. Well, what is the order of this? It's y squared. So if you have 4 derivative, everything will be 0, right? Yeah. Okay. And then the second derivative with respect to y is also going to be 0. But is it going to hold for any value of a02? Yeah, it will. So the first thing always you will do is to check that. Here is simple, and you answer whether this is the case. Yes for any value of step 2. Well, as you may guess, if you assume this area stress function, then you have to the relationship between this function and the stress is something you know. So the first thing is to determine the stress field. So determine the corresponding not a street. So to warm up, why don't you do it yourself? We are considering 2-dimensional case, so we only have sigma x, sigma y1, sigma xy. There's no body forces. My computer is talking to me. You have it? So, what do you see here? What does this stress field look like? Yeah, one thing is sigma xx is constant, the others are 0, perfect. I told you this was simple, but we solved it systematically. What else? Now, rely on your experience as graduate students. What else do you see here? Other than that, it's a constant stress field. Doesn't have to be. Does it have to be tension? Uniaxial. That's what you are jumping the gun. You are going ahead of me. So uniaxial is the point. Only in one direction it is zero. So you basically have to look at your results and make observations. In other cases, things can be much more complicated. I warn you. One observation that you all made is that a stress field doesn't depend on x and y. So a stress field does not depend on x and y. So it's constant. Typically, you may have heard uniform stress field. Okay, and the other is it's uniaxial, right? Only one component is non-zero. So in your other life or in your earlier life, you talked about this as uniaxial, a stress field. Perfect. So we have the stresses. Well, you can guess what comes next. What do you think comes next? Strain. Now you have to tap into the relationships that we developed for plane strain and plane stress. So now you want to have, before doing that, actually, we'll do that too. It's better first to actually look at the domain and look at the boundary conditions. So determine the traction distribution on the boundaries. Of the domain. So we didn't really draw this domain yet, so it's a good time to do that. So we said the Cartesian formulation is best for rectangular domains. So here is x, here is y, and then I call this C. This is L, and let me give some names to these boundaries. So 1, number them, 2, 3, 4. Okay. So and for the purpose of drawing here, let's assume that in the drawing, let's assume that this constant A02 is positive. Okay. So now boundary 1. You now all experts, you can write the traction. You have sigma x x, sigma y, sigma xy. So you know how to write the traction. So boundary 1, how do you represent it? Here x is between L and negative L. y is minus c, and remember this normal to the boundary, so it can be anywhere. So you can very easily write the traction. So for this one I write it so we have the same notation. So Tx, remember, sigma xx nx plus sigma xy ny. And one point here, because some of you have made mistakes in your homework, which I'm grading right now. So n is always outward from a surface. Okay, wherever you have a surface, it's going outward. Even if the surface is inside another object, it's outward from that surface out. Okay. So what is nx here is 0, right? And what is ny? Minus 1. So this is 0, this is 0, this is minus 1. So again, here everything is simple. It doesn't have to be, right? It doesn't have to be always this simple. So this is equal to 0. Which tells you that sigma xy is equal to 0 and sigma yy is equal to 0. In other words, if you want to give a name to the boundary condition of this boundary, how do you describe it? Exactly. So why don't you write the boundary conditions for the other So that's exactly why we are solving this problem. It may look very simple, but you have to understand how this method works. We know the stress field. That's all you know. You have a domain. So you now have to reverse engineer. You have to now see what does that stress field mean. Like what type of boundary conditions is it going to actually bring here. So here, sigma xy is 0 and sigma yy is 0 because we calculate them and they were equal to 0. So maybe that was confusing. So so as a result of that, Tx is equal to 0. I kind of skipped this part. You don't know the surface is free. So again, this is different. That's not your problem. You are making your problem. You are constructing it. With that stress field, you write this. So this is a mistake I have made here. So I apologize. So please correct that, because this is the mistake that I have made, which makes things confusing. So Tx and Ty, this is the equation, right? Now you know that sigma xy and sigma yy are 0. Because of that, Tx and Ty are equal to 0. I went too fast. I thought this is obvious, and that was confusing. We don't know. You are constructing your boundary condition. Thank you, Prabha, for asking, because that made things much more clear. So maybe I should do something like that, right? So I know that sigma xy and sigma yy are equal to 0 from the area stress function, and because of that, Tx and Ty are 0. And since there is no traction, this is a traction-free boundary condition. Is this now clear for everyone what's going on? Draw do things systematically. For the second one, which is to the right, x is L, y is between C and negative C, and this is N. So nx then is equal to 1 and ny is 0. So if you write Tx is equal to sigma xx, right? And we have the equation up so you can see, and Ty is equal to sigma xy. And sigma xy is 0. Sigma xx, we calculated this before. So it was from here, you know that it is 2 times A02. Okay? So, and this is a constant, right? So boundary 3 is also traction free. Maybe I write it down again for the sake of completeness. Your job is now to check that I'm not making any mistake because I'm just writing things. They are both equal to 0. So we have traction free again. And finally, the boundary number 4, which is on the other side, what do you have for that? Tx is exactly -2 and Ty is 0. Okay. Now, if you assume that A02 is positive for the purpose of drawing, just draw these boundary conditions that we found. I mean, traction free, there is nothing to draw. You have it? Does it have values on everything? So it's constant, right? If it is positive, it looks like that, but it could be also negative. So just to make sure, the value is 2A02. It could be positive or negative, then things will be reversed. And what kind of problem is this? It doesn't have to be tension again, right? Exactly. So you have uniform tension. It's a useful problem, a simple problem, but a useful one. Okay, so now we know more about it. So what is the physics of this problem? So remember what happened. We started in the dark, and then we found out that this phi, particular phi, describes a uniform traction distribution in the x direction. It's uniaxial. And we also know the magnitude. So a problem which looks like this. So remember the area stress function? What was the form of this function? A02 y squared. Now you know that the coefficient of that, A02, has what kind of an object, has what type of meaning? Yeah, in this context, it is related to the magnitude of the force that basically you are applying to this rectangular domain. A little bit of physical meaning for that.
So if that's the case, why isn't A over C? It's sort of a distributed force.
Over C.
Yeah.
It's not, so it is, so basically this is the traction. So the force is going to be the integral of that.
Right. You show it's a distributed force.
Right.
Okay.
Does it make sense? The traction, the definition. Yeah, but remember the definition of traction. How did we define traction? Was it just force? Exactly. It was always force per unit surface. And the body force is also force per unit volume. So it is really traction. But now, continuing on what Tony said, if you use Saint-Venant principle, you can say that this problem is equivalent to the problem you all thought about long time ago, right? This problem. So if you are far from the boundaries, this is similar to a problem where you have a concentrated force you are applying. It can be in this direction or it can be in the other direction. This direction is arbitrary. And that would be the a statically equivalent force to what you have here, right? Which is, if I want to write it in a general form, it would be the integral of this traction you have here, right? dy. So, we are not done. So now we have to go to where I told you to go a few minutes ago. Now that we have figured this out, let's take that t is equal to 2 times a0t. If we assume that, then sigma xx is simply t, sigma xy and yy are 0. And now we want to find the strain solution. Because we never really solved a problem to the end, and we want to now solve it to the end. So step 4 is find the strain solution. And let's use plane stress formulation. Good time to have you do something to make sure that you're not sitting here. So remember what we did. So we started from biharmonic equation. We assumed a certain field. Generally, you have to make sure that it satisfies that equation. Then we got the stress field. Then we looked at our domain and we built our problem by looking at the boundaries to see how things look like. And now we want to know more. We want to know strain and displacement also, to see whether all the things that we learn in elasticity is going to actually produce the solutions that we need. Now let's use plane stress solution and go from a stress to displacement, to a strain first. where are those equations? Okay, let me ease your pain and give you the formulations. This is the one that I recorded, so so take sigma x equal to t, so don't carry the 2a02. Just substitute. I expected some very happy, like, yes, you see that things should look very familiar to you, right? Now, if I gave you a simple biaxial problem, you would all know how to calculate the strain. It would be really bad if we are here and this will not match what we would expect to see. Right? But you see that using this very general machine for this simple problem, we get what you expect to get. You get the force divided by E, that's you get the strain, and then minus nu. And finally, we have to calculate the displacement. So step 5, which is the last step, is using the strain displacement relationships, find the displacement solution. So I hope that you all remember the strain displacement relationships, right? So E, let's start with that. So U comma X is T over E. So what would be U? Is that R? Is it a constant? It has to be it can be a function of Y, right? So this you remember, so it was just a review from your calculus. I think you all have done this before. And we can do the same with, I use EYY first for the reasons that you see. So let's do the same for V. And nu is the Poisson's ratio. So then we have V And now it can be plus a function of x. What haven't we used? EXY, which was 0. But it's useful. So EXY is 0. Written something in Spanish here. And so EXY is 1/2 u comma y plus v comma x, right? So if this is 0, u comma y plus v comma x has to be 0. And if that's the case, now we know u and v, the general formulation. What can you say? F prime y plus g prime x equal to 0. And f prime and g prime here is the derivative fy with respect to y, fx with respect to x. And if we have this situation that you have a function of y which is the derivative is equal to negative the derivative of gx, which is a function of x only derivative. What is the only possible way for this to work? 0? Why do they have to be 0? They have to be constant, otherwise you cannot have y equal to x. If you have y on one side, x on the other side, there's no way you can satisfy. It's only possible if both are constants, right? And we take this constant for reasons that we will see later, negative omega 0. So if we do that, then we can have a relationship for fy. Then it is simple. And gx would be, now u0 and v0 are also constants. Gerald, convinced? So the first two part is simple. Then you have that fy and gx. Then we know that exy is equal to 0. So if you substitute, you get that relationship between y and x. You know that f is function of y, g is function of x. Their derivatives will be only also functions of y and x. Now, for them to be equal, or the summation be equal to 0, or one be negative of the other, the only possible way is that they are constant. Does it make sense? So one should be like, I don't know, c, the other would be negative c. Nothing else would work. I'm sorry. No, why? So these things are, they have to be equal in the derivative sense. Now, when you go one step to the functions themselves, then you get those constants, and those are free to be, but they are constants. They cannot be now, they're just constant, not a function of x and y. Convinced, Prabha? Oh, it won't be that different. So you remember the biharmonic equation is the same. So then the formulation would be different. But in terms of solution, it won't be that different. Are you trying to get something about tomorrow's exam? This doesn't seem to be a question about this part. It's about the candidacy exam. Is that true? No. Don't worry about it. Just have a good night to sleep. Have good breakfast. Make sure that you don't make silly mistakes. I gave the same advice to Tony, who also opted. He opted to have elasticity questions in his exam. So, right? Good night of sleep is important. Try to sleep. No, honestly. Try to eat definitely tomorrow. Bring a snack. These things are important. Don't try to figure out what the questions are. Projection. No. Don't worry about it. Okay. Besides that, we have this. Now comes the interesting part. Now we have fy and gx, so we have the full form of u and v. And we have something to discuss about, because it seems that things are a little bit more complicated than you expected, right? This is a very simple problem. So I write u, it's tx over e, and then right, and v write things nicely. Yeah. Okay. And we chose omega 0 arbitrarily, no? You agree with me? This just came from nowhere. And we have now u0, v0, omega 0. So what's going on here? Why then we ended up now with, after all of that, with a displacement field which is not even constrained? What do you see here? Let me help. Prabha, did you have a... No? So let's just look at now the tx over e, and this part is kind of clear. What is not clear is kind of this part. What is going on here? So, giving you a hint. It is. So remember long time ago when we looked at the gradient of displacement and we separated a part which was symmetric and then a part which was anti-symmetric. This is one thing I want you to remember. And then later on, I didn't prove it, but I showed you a theorem about the uniqueness of the solution in elasticity, boundary value problems. What did I say there? I said if we have two sets of solutions, strains and stresses, they have to be the same, they're unique in boundary value problems with the same boundary conditions. But how about displacements? They don't have to be unique, they would be equal up to a rigid body displacement, some rigid body motion. Why? Because rigid body motion doesn't create any stress or strain, so it is there. So we kind of expect that. Now, if you take the gradient of just this portion of, forget about the Tx over E and Ty over E part. If you look at the gradient of this portion, how would that look like? So remember, derivative with respect to x, y, x, y. How does it look like? So it will be here 0, negative omega 0, omega 0, 0, right? How does it look like? It is skew symmetric. It is that infinitesimal rigid body rotation we talked about before. So you can't constrain it. So your solution is unique up to this point, and you see why. So that was the fun part. So I write this, so later on if you look at your notes to remember what we talked about. So that remember that the uniqueness, so I couldn't get a unique solution. The uniqueness is up to this rigid body displacement. So the uniqueness of the solution to boundary value problems. Oops, what is this? Is up to an infinitesimal rigid body displacement. So omega 0 cares for the rotation, and then you have u0 and v0, so you can have translation in x and y. You can't constrain that. So how did we always constrain these kinds of things? If you wanted to have a unique solution, what did you do? Let me draw the domain again because I need it. I suggest you to do the same with your domains. So here is the problem I created, starting from a very, very simple area stress function. Very simple. Here is x. Here is y, and then at the end I saw that I ended up with 3 arbitrarily chosen constants, so I don't have a unique solution. How do I get these 3 constants? How do I make sure that my solution is unique? Boundary conditions? But we already have, we did everything. Boundary conditions are fraction free, and then you have uniform fraction on both ends. These are boundary conditions. What? I'm sorry. Initial conditions. That's more like for a dynamic problem, right? When you say initial conditions. What do I do physically? What would you do? Yes. You have to hold it. How did you hold these things before? Guys, you have seen this in mechanics before. Yeah, you have to fix it somehow, right? So you use some sort of fixation. You remember those rollers, those stuff that you use, All of those is to basically fix those. Those are called fixity conditions. So to determine basically the constants we need fixity conditions. How many? Yeah, we have 3 things to, that's why I left this. So we need 3, right? And what did you do before? For example, you fixed it somewhere, and this gives you what? 2, right? You said, okay, u has to be at point 0 and 0 has to be 0, and v also has to be 0. And then, for example, you put a roller somewhere. Right? And then you said, okay, at that point, it cannot go in the y direction, but it is free to go at L. Yeah, this we called L. L and 0 is 0. So if you fix it somewhat, yes. Yes. Yeah, let's look at the equations, then it becomes clear, because this is a rotation like this, the whole thing rotates. But this is, we are not, we everything we keep in its place. So we don't, you remember in the very beginning I said we don't consider anything which is rate dependent. And we took the acceleration b equal to 0. So either things are quasi-static or static. No. The whole thing can rotate. Maybe I'm not sure what you're asking.
It's not an issue with the class, it's an issue with the assumption. I think we got it.
But this is a static problem. We started, we put everything equal to 0 in the beginning, right? Sure. Gerald, did you have the same question? Well, acceleration is not something we have considered. We have taken acceleration equal to 0. But this rotation is not going to generate a strain. This we decided on early on, right? I showed you that. It took us one class to show you that this part, all the strains associated to that will be 0. You remember when things rotated and then we said, well, are the lengths are going to be different? Are the angles going to be different? If everything is rotating together, and if this is the case, you cannot have any strains. So if you have no strains, then you have no stress. Maybe Tom, we can talk about it afterwards. I'm not sure. Yeah, I'm not sure this kind of rotation. This is really rigid body rotation. That means the whole thing is rotating together. Remember this square we had when I drew it painstakingly? and it became like this. And then we said that if everything is small, the lengths won't change, and the angles, of course, won't change because you have the same theta here. And then we decided that this part of the displacement gradient is not going to generate any strain, because a strain is either you are changing your length or you are changing the angle, and it was not doing anything of that. And this is this kind of rotation, but we can talk about what you are thinking about. Anyway, I thought you are all going to be very excited to see that from a very general formulation, you kind of, and at the same time you can see that even a simple problem like that, you know, it's a lot of calculation. That's why we cannot do something more interesting in the class. So we have only a couple of minutes, so I don't want to start the second problem. So we are going to do another a little bit more involved example next time. And if you have any questions, now you can ask me.